Thermal comfort is probably one of the biggest reasons why we people build buildings. Living outside sucks in a large part of the world. So we invented buildings kind of to protect ourselves from the elements out there. In this analysis, we used the comfort criterion as defined by PHI and Fuse, which addresses the lack of radiant asymmetry. In other words, it ensures that all of your surfaces inside the building have temperature close to one another, so you don't have much asymmetry, therefore you feel comfortable. It also eliminates or addresses downdraft. Downdraft is when you have air inside the room that gets close to the interior surface of the window, that gets cooler. There's a downdraft that brings the cold air down to the floor, and that leads to more discomfort. So both PHI and Fuse, in other words, both passive standards, have criteria to prevent this in slightly different ways, but basically the comfort criterion is based on avoiding radiant asymmetry and avoiding downdrafts. Similarly, making your building more airtight addresses drafts because it eliminates or significantly reduces the cold air coming in. And by that, it also makes your air temperature more even from the bottom to the top of your building, so your feet don't feel as cold while your body is warm. Passive building standards, as I said, have similar requirements for both comfort criterion and air tightness, yet slightly different. We're going to see what that looks like in the next videos. Other building standards, most of them address air tightness, except California Title 24. We're going to see that in a specific video. No standards other than PHI and Fuse have a comfort criterion. So that is something that we're going to account for in this scoring for thermal comfort. This big table shows requirements for fenestration, basically the U value required by different standards. On the left-hand side, the brown cells show the uninstalled requirements that all building standards except PHI have. And on the right-hand side, you see that PHI is the only standard that prescribes an installed value. Difference being that in calculating the installed U factor, you account for the thermal bridging that exists at the interface between the window and the wall. It's not leakage, it's not errors on the install. Even if your window is perfectly air sealed and perfectly installed, there's a thermal bridge that causes your window to underperform compared to the label uninstalled value, and that is what PHI uses in determining the U value required to meet the comfort criterion. The results, we modeled all different standards in PHPP, and we assumed an installation thermal bridge of 0.04 watt per meter Kelvin, which is very generous for non-passive standards, but we wanted to keep it simple. The installed U values were calculated in PHPP, and the average window surface temperature was calculated from the design conditions. And this is what it looks like. At the bottom, on the x-axis, you have the exterior temperature, ranging from -25 all the way up to 45. Again, we have 50 different projects ranging from Florida and Texas all the way to 10,000 feet of elevation in Colorado. And you see the comfort condition, you see the average, each dot in this graph shows the calculated average temperature on the interior surface of the window based on the project-specific design temperature, as well as the U values that each standard mandates that we saw in the previous slide. You see that both PHI and Fuse kind of follow the same principle. The orange horizontal line shows the kind of the threshold to target for, where the temperature delta between the room average and the window surface is less than 7.6 degrees. And you see that more prescriptive standards such as Pretty Good House and the IECC fail at meeting that because they are more prescriptive, and so they don't really address comfort criteria. In average, this is what it looks like. In average, you can expect a delta temperature of 14.3 degrees if your building is built to the 2018 energy code. And if you're building to the 2021 energy code, it gets tiny little bit better. The delta is 14 instead of 14.3. It is still too great to be comfortable compared to the maximum allowed delta of 7.6 degrees that it is represented by the orange line in this graph. You see the Energy Star is a little bit better. You see the DOE's energy rate is not much better. California 2024 looks better out of the climate is very mild. So their prescription does not really make too much of a difference. For scoring, this is what it looks like. We define the two criteria to be the delta T between the window surface and the room average, and then the air leakage reduction compared to the 2018 energy code. 2018 energy code is the baseline across this study. So the delta T reduction, it creates a more even thermal environment. And then the air leakage reduction is the reduction compared to the 2018 code, and it eliminates drafts and introduces the air certification within the building. So you're going to have the similar temperature between your feet and your head. And this is what it looks like for scoring. Again, this is a scoring that we made up in trying to compare the reduction of air leakage to temperature on the window in the same value for thermal comfort. And we're going to see this for other criteria throughout the study with the summary at the end.